Next session is a series of 6 lightning talks from AI Rising Stars. These are students, postdoctoral fellows, researchers who, while early in their careers, are already making an impact in AI. We'll have to be quite strict about the timing, so 5 minutes of a talk, and then we'll have 3 minutes for questions. And then you will have an opportunity to interact with the speakers in the poster session. So each of them will have a poster during the poster session that follows. All right? And we do have one slide change. One of the speakers unfortunately had an accident and couldn't come, so she will be presenting virtually. We'll keep her at the end of the session. So with that, the first speaker, Zhijing. She is a final year PhD student at Max Planck Institute and ETH, where she works on socially responsible NLP by causal inference.
Thank you so much, Rada, for the very warm introduction. Hi, everyone. I am Zhijing, and today my talk will be about causal NLP and the way towards social good. Let's start our journey. So, as we all know that natural language models have made impressive progress these days. So we can see a huge map of large language models building by different parties and attracting famous attention. And very likely, all of our parents, family, friends know the word ChatGPT. So what we argue is that despite all these impressive progress, the current LLMs are still like alchemy. So why do we draw this analogy? Similar to the spirit of the stochastic parrot in the previous talk. If we look into, for example, several hundred years ago, see a shelf of chemicals, then we see names such as spirit of salt, angel's glow, lunar caustic, and so on. So these are all real names that time. And there are two problems at that stage of exploration. First, they do not have the right representation to start from. Second, because of this, they cannot find the correct causal mechanism behind the reactions. Similarly, if we look into the prediction of large language models, we can say that, for example, if we give them a simple addition question, 5 plus 5 equals what? And it didn't build it the same way as how humans reason. Instead, as a probability distribution of this 5 plus 5 correlate with 10 by what probability, correlate with 15 by what probability. So this also blocks LLMs from obtaining the correct representation, not to mention the causal mechanisms. So what we do is to draw an analogy from how alchemy is broken into modern chemistry, where the spirit salt is actually the hydrochloric acid. And then what we also want to do is to break LLMs from correlation machine into causal models. So using the tool of causality, we enter into NLP by 3 different aspects where we look into the core methods of causal inference, apply them to build robust and fair NLP, and also apply causality and NLP together to analyze social phenomena. With more details later in the poster session, here I just gave an overview. Our approach into more robust NLP is to use the framework of structured causal models, where we know that when humans make decisions, they have a certain way acting according to a certain causal model. And what the model do is it establishes certain spurious correlations, and then its prediction Y is maybe based on both the real cause and the spurious correlated Z variable. And then we formulate everything as the discrepancy between the human causal model and the model learned model. And then using this as a framework, which guides many of our work on stress tests for NLP, resulting into TaxFulla, which is the default method for the tax adversarial attack now, and with various studies applicable into classification, natural language inference, sentiment analysis, math reasoning, and so on. So, and we propose that the correct way to build more robust model is to make the models learn the causal mechanism, which induces the lowest Kolmogorov of complexity. And we try to encourage the model to learn a mechanism that's faithful to the human causal graph by enforcing conditional independence and a bunch of constraints. Lastly, using both of them as tools, we also extend into various social applications combining causality and NLP together. For example, we apply them to analyze policies where we see how social public opinion affects the social distancing policy in the age of COVID while controlling for the case numbers. We also apply that to analyze gender bias by building counterfactual models of how would a man act in the same scenario. So zooming out, our vision is to extend all these methods for various social good applications. And our roadmap is to start from technical causal methods, extend to robust and fair AI, and finally, in understanding social phenomena in terms of cause and effects. And all these work are having credits to a nice team of collaborators. And thank you, everyone. Welcome any questions.
Questions? One quick question on how you interact, since all this is also having impact on these other disciplines, how you interact with people in, for instance, political science or healthcare or in other disciplines, and what are ways in which these causal methods can leverage knowledge from other domains?
Yeah, so I think this is a great question. What we see in all these past collaborations is that we really need to know the vocabulary of people from other disciplines as well as the question they care about. So we actually spend a lot of time formulating the causal graph together with domain experts. Yeah.
All right, so there will be more time for questions during the poster session, so please visit Zhijing's poster. Right, so our next AI rising star is Guandao Yang. He's a postdoctoral fellow at Stanford University, where he works at the intersection of computer vision, machine learning, and computer graphics.
Sure. Thank you so much for the kind introduction. So today I'm going to talk about how to use neural network and Monte Carlo method to solve PDE. So PDE is an equation that involves partial derivatives on one or the other sides, and they are language of physics, and they are very useful tools for scientific computing, including vision, graphics, and simulation. So traditionally, when we want to solve a PDE for a complete domain, we need to first discretize the domain and then define a basis function so that we can resolve it into a linear solve system. So while this is fast, discretization turned out to be very difficult. So state-of-the-art discretization methods can take hours to run, and even one very simple mistake like this could lead to numerical errors. So this begs the question, can we solve PDE without discretization? It turns out that both graphic and machine learning community has come up with some solution. From the graphic community, people try to use Monte Carlo method, which they turn the PDE into an integral equation and then use Monte Carlo integration to estimate the solution. In machine learning community, people try to train a neural network to enforce constraints imposed by the PDE. It turns out that these two types of methods have their own pros and cons. In the Monte Carlo method, while they are provably unbiased, they could usually experience high variance during inference time, so it could be slow. On the other hand, the machine learning method usually are very fast in inference, but it could be biased because we don't know the training loss can be zero. So my works kind of live in the middle. So our hypothesis is there is a way to combine these two classes of method to provide a faster and more accurate solver. So to take a deep dive into it, so if we look at a Monte Carlo solver for the Laplace equation, the intuition is like in order to grab the solution in the middle point, we will randomly sample a bunch of points on the sphere and then aggregate the influence of the solution from the sphere. So if the point hits the boundary, then we can query the boundary solution. But if it doesn't, so the best result we can go on to is to recursively call the estimator, and this could lead to a very, very long recursive call. That's a source of high variance and slow inference. So in our method, what we hope is to cut the inference and stop the walk and query the neural network. And we hope the neural network can approximate a solution and provide fast inference. How do I get a neural network that can approximate a solution? Fortunately, the Monte Carlo solver itself is able to provide unbiased solution. So we can use that to generate data to train such a neural networks. So the method is very simple, but we are able to get about 10 times speed up compared to the Monte Carlo methods. We are more accurate than the neural network methods, and we don't experience the Monte Carlo noise as the state-of-the-art Monte Carlo methods. So one limitation for this kind of hybrid solver is still bias. As you can see that as the number of inference walks increase, this curve plateaus instead of going to 0. So this is not ideal. But we actually are able to solve that by using a neural network not as a cache to stop the walk, but also as a control variance where we can result in both a fast and provably unbiased solver. So as you can see, this loss goes to 0. So to summarize, so my work's trying to combine this advantage of neural networks and Monte Carlo solver. And this hybrid solver is very scalable with compute, and I do believe that there's many more to be done in these directions. So thank you so much for your time, and I'm happy to chat more in my poster session. Thank you.
So you mainly hinted at future directions. Can you say a little bit more about what would be some ways in which this could, where you could take this on?
Mm-hmm. So I think one of the most exciting future work directions is to extend this to a wider range of PDE. For example, most of the physics equation is much more than a linear equation, elliptic PDE. And what we'll be interested in is, like, for example, are we able to take the existing math development of integral equation and then expand it to larger family of PDE that can actually help physics. But I think this is very promising because it's very scalable with compute, and I think we will get more compute in the future. Yeah. Thank you.
All right, our next speaker is Yildirim from the Human-Computer Interaction Institute at Carnegie Mellon University. Her research is on providing support for cross-functional teams to envision AI experiences and interactions.
Thank you for the lovely introduction. Hi, everyone. I'm Noor. Very happy to be here. So I do human-computer interaction research, and my work is really complementary to the work that advances new AI capabilities. So my focus is really on taking these existing AI capabilities and applying them in the real world in ways that are useful for people. So we've seen like an incredible amount of technical advances in the recent years. Our computers can now translate between languages, complete the code we're writing, and driving our cars. But while these capabilities are becoming more and more available, making them useful in the real world remains really challenging. Today, nearly 90% of AI projects fail. And one of the main reasons is that innovation teams are really doing a poor job of envisioning and selecting concepts to develop. So like that example of that startup trying to replace user research with LLMs, like that's a really bad idea. So teams really tend to focus on high-risk projects that might or might not be valuable. And they also tend to really think of AI innovation as a technical challenge solely, and they tend to sort of disregard, is that prediction useful for a person? Is it solving a user's problem, or is it solving a business problem? So when I talk to practitioners, people like product managers, UX designers, data scientists working at large tech companies, one thing I repeatedly hear is that data science teams envision things that users don't want, and design teams envision things that can't be built. So there's this gap between AI expertise and domain expertise. And especially people who don't have a technical background in AI, they really find it challenging to understand what is it that AI can do and what kind of predictions they can ask for. And they really want resources that help them with ideation and problem formulation. So they want to know what AI can do instead of trying to understand how AI works. And my research is really about trying to build that kind of resources. So I created this AI brainstorming kit that captures AI capabilities in non-technical terms. So I've looked at 40 real-world AI applications across 14 domains. So things like spam filter, text generation, fraud detection, and so on. And I analyzed these and distilled them into 8 high-level capabilities. And it's sort of like a taxonomy of what AI can do, along with example applications in the real world. And then I started to use this as a tool to conduct brainstorming workshops with interdisciplinary teams. So one of the teams I've been working with is a healthcare innovation team working in the intensive care unit. So they're looking for AI opportunities. They had this big data set, sort of similar to the Mimic data set. And taking this sort of capability-driven approach, along with examples, really scaffolded doctors' and nurses' understanding of what AI can do. So when we were brainstorming, for example, we used the example of Amazon's anticipatory shipping. So they know what people will order, they pre-ship it, so when you order it, it arrives quickly. And we were thinking, can we use this sort of capability in the intensive care unit? And doctors and nurses came up with this idea of, okay, like we order medications from the pharmacy every day, and sometimes we have to wait like 3 to 6 hours. And these patients are really sick, so you need the medications right now. So can we look at a group of patients in the ICU and try to predict what kind of medications they will need tomorrow? So if you think of this, that's like relatively low risk because you're sort of stalking, you're not administering medications. So compared to like trying to predict what's the optimal dose for a single patient, which is like really hard to model and also can be really harmful if things go wrong. So the message I want to leave you with is this. Improved ideation and project selection can really help innovation teams in identifying low-risk and high-value AI use cases. And thinking about responsible AI, this is a great moment to actually consider risks with a broader set of participants and stakeholders. So how do we actually generate many AI concepts and assess their value against their risks simultaneously before we actually select something to build? Thank you very much. I'm happy to chat during the poster session. Thank you.
Well, that you covered this topic. This is all great, but especially in medicine, you also have FDA regulatory. You also have, usually these technologies have to be turned into products, so they should be profitable in some way for somebody to pick them up. Have you thought of those aspects, and how do you bring that aspect into when you're deciding what project to?
Yeah, great question. So I think the way I try to think of assessment of a concept is thinking about risks. So is this technically feasible? Is this desirable by the end users? And is this financially viable? And one of the risks is, as you mentioned, like the regulation, like what are the potential harms? Is this actually So I think it's between like, is this feasible, or like, is this also desirable? Also, like, what are the harms? But I agree, like, healthcare is like really hard to deploy things. But I think one thing I'm trying to really explore is that, can we really stay away from things that are hard? And that might be a way to sort of, like, if we are not giving a drug to a patient, that's like probably requires less regulation. I'm just like looking at the pharmacy stocks, right? That's not directly giving something to the patient. But yeah, great point. Thank you.
Right, so our next speaker is Lu Mi. She's a postdoctoral fellow at University of Washington, also a fellow at the Allen Institute for AI, and she works on neuro AI, which explores the intersection between natural intelligence and artificial intelligence.
Thanks a lot for the warm introduction. By clarifying, I'm actually from the Allen Institute for Brain Science, which is slightly different from the AI too, but it's okay, yeah. So first of all, I would really thank the invitation from the organizer. It's really a great chance to speak here. So my research focuses on bridging the gap between biological and artificial neural networks. So as many of us today are really excited about is those large language models, and they have extremely large scale, but also to show the emergence of intelligence. Well, there's another kind of intelligence that we are all familiar with, that is our human brain, which has even much larger scale. But surprisingly, our brain was performing in a much more energy efficient and reliable way. So that naturally leads us to think about whether we can inspire from our brain to help develop the next generation AI. But unfortunately, it is very challenging because our understanding of a brain is still very little. So the first barrier is to think about the scale of the problem. And then one of my research focus has to be really think about how we can use advanced AI tools to help develop scalable and efficient automatic pipeline for brain discovery. And to address this need to put the scientists in the loop. So we have been able to use AI tools to help speed up and scale up like the accreditation and reconstruction pipeline for mapping the brain connectivity. So even then, we're able to get much larger scale data, but then the real question is still how we can understand those neural data. So my research focus has also been trying to using artificial neural network and to help understand the brain functions. So we're utilizing a lot of like deep learning tools, but also which gives us the chance to build like an in silico digital twin of our biological organisms, and it will allow like very flexible study and to distill knowledge, learning reasonable representation, and as well as to develop new hypotheses. And also you can think about actually how different these two network systems are. They might look similar at the very first glance, but our brain is actually performing in much different ways. The basic computation is in spike versus the rate-based network, which is in a highly sparse and stochastic way, which actually build like a solid foundation to be why the brain is very efficient and robust. And secondly, there's a very diverse cell type, diverse coupling, and those activity and coupling was involved in very diverse timescales. So although there's a mismatch, but people has really been able to show you can even using an artificial neural network like a recurrent neural network as a good predictor of the neural dynamics. But there's lack of interpretability that neuroscientists really want to understand this in a much more mechanistic and biophysics way. So they have this biophysics model. You can even put a lot of like biodata, like the connectivity and cell types into the constraint. So, but those models are usually hard to fit. So in order to balance the trade-off, we are using the biophysics model as a generatory model to generate a prior distribution. And then we jointly maximize the data likelihood and also reduce the gap between our prior and the posterior and able to balance this trade-off. So in another kind of application, we're interested and want to know how we get meaningful representation from this massive, noisy neural activity time series data. And to get useful representation, for example, to indicate like cell type information in. And given the knowledge that cell types don't really change across the development of the cell, So actually, we're giving this time invariant constraint by adding an external time invariant parameter that will be jointly optimized with this dynamical Causal model, and which can be arbitrary like a RNN or even transformer. So, and then we successfully able to decode like cell type information from this time invariant parameter. So I think then the last important question is to really figure out this universal principle across animal or even across species. And finally, even to think about at what level of abstraction even we can align these two systems. And even how we can really inspire from brain, but there's so many interesting properties that the AI model today don't have, and to improve their efficiency, robustness, and interpretability. So one of my prior work is trying to show there's an advantage of this algorithmic advantage to mimic the stochasticity of the brain computations, which we have been putting a randomness into like already trained model, which for depth estimations as an example, and which is originally not stochastic but deterministic. We show there's a benefit to estimate the uncertainty during inference time without retraining or retuning, and surprisingly, this uncertainty map is very correlated with the error map. So I think an important fact of the responsible AI is to make sure this uncertainty level is well calibrated and to make the model not to be overconfident. So to summarize, as you can see, I think there really should be a loop between these two networks, and we should bridge the gap, and which can benefit in both directions. And that kind of be summary of my journey, which is the benefit from collaboration across discipline and institute. And I really want to acknowledge the great support from my mentor, collaborator, and the funding. So thanks for your attention, and really looking forward to have more conversations. Thanks.
So our brains are made of cells, and artificial AI are made of silicons. I wonder that like most of the research are done to make the silicon network looks like the brains one. I wonder, is there another ways around, like for example, trying to program biological cells?
Oh yeah, I think if you're talking about how we can making the biological plausibility into really building like a AI architecture or even hardware, I think there's a lot of interesting study. People are building like a neuromorphic chip, which also like to replace like the rate-based neural network by spiking neural network to really show this benefits of efficiency. So this is a very active field, and a lot of people are really, I'm also very interested in it. Thank you. Yeah.
So next we will hear from Gengshan Yang, who is a research scientist at the Reality Labs in Pittsburgh, and he works on intersection of computer vision, graphics, and machine learning.
Okay, hello everyone, my name is Gengshan. Today I'll delve into our work towards 4D reconstruct in the wild. So the work is primarily done at CMU with collaboration with Google and Meta. So what is 4D reconstruction? We might be more familiar with 3D reconstruction, which reconstruct the 3 locations of points and their colors. For 4D reconstruction, we also care about temporal changes, for example, motion. Those high-quality reconstructions are often requires a capture studio, and those capture studio are especially they're built. They're not only costly to build, but also, more importantly, they cannot capture the diversity and richness in our real life. For instance, natural phenomenon or outdoor activities. On the other hand, there exists a lot of videos in the wild. For example, those ones we took for our past and family members, and those on the internet. These videos provide rich signals about dynamics of the real world, but are largely underexplored for reconstruction purpose. And our goal is to unlock the capability of reconstruction algorithms on those in the wild videos. To look into the challenges for reconstruction in the wild, for the videos we captured in the studio, those are pretty much structured. We have cameras that are pre-calibrated and synchronized in time. On the contrary, for the videos we capture in the wild, those are unstructured. They can be taken at different time and with unconstrained locations, which makes the problem challenging. To tackle this problem, we take inspiration from analysis by synthesis, which provides a framework to build a model that is faithful to the data, but also we're able to inject flexible priors. The idea is pretty simple. We can think about reconstruction as an inverse graphics problem. We can first synthesize a video given the current reconstruction, and then take the difference between the rendered video and the input one. And the difference will guide us to improve the 4D reconstruction until we're at the point where the reconstruction and the rendered the input video are indistinguishable from each other. So here we want to pull the cat closer and make it smaller so that the limbs are visible. However, colors is not a good metric for reconstruction quality due to the ambiguities in appearance, viewpoint, motion, etc. For example, the reconstruction might look reasonable from the reference view, but if we view it from different viewpoints, they might look pretty much distorted. In order to regularize the problem, we consider two types of generic priors. One is foundational vision priors, for example, motion correspondence, surface normal, and self-derived features. And those provide signals about the shape and motion on the object surface. Besides the image-based prior, we also consider physics priors. And those priors tell us whether a 4D reconstruction is physically plausible. For instance, the reconstruction of this dog should stay stable and not fall over once we release them. So combining those principles, we built algorithm to reconstruct 4D instances from in-the-wild videos. And our method works for a large variety of object categories. We could also render the video after reconstruction from a fixed time at different viewpoints or render the motion at a normal viewpoint. And this method can be extended to reconstruct a complete 4D scene. And from those reconstruction, one could think about creating new videos from extreme viewpoints. For instance, if you look at this blue camera, which captures a third-person view as if a human is walking the dog. We could also render an egocentric view as if the world is seen by the dog. And finally, a bird's eye view as if a drone camera is filming the whole scene. If we have multiple actors in the scene, we could think about synthesizing interactions from an egocentric view, such as me patting my cat. Okay, so finally, we do not only want to make the reconstruction visually plausible, but also want to make it physically plausible. By jointly optimizing contact physics and dynamics, we can make the reconstruction can be replayed in a physical simulator. And such physically plausible reconstruction are easier to be transferred to robots, and we can help the robots to acquire natural motion skills from in-the-wild video footage. In the end, I want to try to deliver the message that the 4D reconstruction in the wild is an interesting problem and has a lot of broader applications. So we hope to release the toolbox to help people delve into the problem and see what can we solve together here. Thank you.
Because the physics priors.
Okay, so for that part, we think about how do we, so basically we use a differential physics simulator. So once we have a 4D reconstruction, you could use that as a reference trajectory to infer what physical signal do you need to drive such a generation of those 4D trajectories. And we solve the differential simulation problem together with the differential rendering problem by coordinate descents. So there will be a poster later to talk about that work.
All right, thank you. So our final speaker for this session is going to join us over Zoom. Her name is Aadirupa Saha. She's a research scientist in the Apple Machine Learning Group, where she works on large-scale robust algorithms for sequential decision making.
Hello everyone. I hope I'm audible. Actually, I'm sorry, so I'm not able to understand if I'm okay. I believe I'm audible, and I'm very sorry I could not make it in person. I was supposed to come in person, but I had an accident yesterday, so on my way to the airport. So I am so sorry, but I'm possibly going to be around tomorrow. So if still someone wishes to speak and discuss, I'll be very happy to. So this talk, before starting the talk, I'm currently a research scientist at Apple. I have been, I did a short visiting faculty stint at TTIC last year. Before that, I was a postdoc at Microsoft Research. And my research interest broadly includes machine learning theory, algorithm design, differential privacy and stuff like that, federated learning and differential privacy. So major focus of my work has been to design effective prediction models, which are more human-aligned prediction models. So what does that mean? So there are humans, there are machines, and then there are machines which are designed to work like humans, or that's a broad goal of AI, to actually build systems which can act more like humans or understand the decision-making process. So that's what we call as human-aligned prediction models. So why and what? So what is a prediction model? That's very easy. It's basically a mapping between a context to a decision space. So for example, in earlier days, the prediction models used to be very simple. Say it is a spam filtering process where the context could be an email, and the decision could be whether it's a spam or not spam. And basically, the prediction model is just given a context maps whether it is spam or not spam. It's kind of a binary classification problem. Now, in modern machine learning systems, in modern days, as we try to deploy our machine learning models to much more complicated tasks, starting from healthcare to stock market to robotics, autonomous driving, weather prediction, recommender systems, fraud detection, and all the recent madness about large language models. These are really hard, complex prediction tasks. And we need to understand how to build these prediction models more according to the need of the humans, because that's what ultimately the objective is, to serve us better, make our life easier through this AI systems. So for example, if we consider this example of ChatGPT, it's essentially a prediction model where the contexts are a set of bunch of occurrences of previous words, and maybe the question that was asked by the user, and the prediction model is and the prediction space, or the decision space, is essentially a bunch of words that can occur given the context has been there. The context, given the context, what is the most plausible next word the system can predict to come up with a coherent piece of text. So that's kind of a prediction model for ChatGPT. Now, why do we require human alignment here? Because suppose I am using ChatGPT, I have a particular way of speaking, I have some tonal preferences, I have some language preferences, some vocabulary preferences, and writing preferences. So the system needs to understand what do I like, how do I write, or my writing style, and it's very personalized, it's very individual. How do a system actually would understand and personalize it based on my interactions? So for example, if I want it to summarize some piece of text here, maybe there could be 3 or 4 possible ways, or even more than that, various ways you can do a text summarization. But how would it learn that what is actually the summary that I would like the most, or how I would write the summary based on my language preferences? So that's where the requirement comes for human alignment of prediction models. And before designing the systems which can actually understand human needs and personalize based on the particular user who is using the system. We need to understand how we humans are actually making decisions in day-to-day life. We, starting from the very morning in our life, we make probably like thousands of decisions, if not more. For example, many of you actually commuted today from the hotel to the venue, or maybe you're just your home to work, and maybe you drove on the way. You asked Google Maps to figure out like what is the most possible, what are the few options, few ways I can drive through, and maybe it will show you 3 options. Now, how would you make this decision that which is the route that you're going to take? Possibly you will just evaluate it in your head that, okay, there are these 3 options. I see this has the lowest commute time, and this has the lowest congestion time, and possibly it's going to be also most time effective, it's a better environment. So I relatively prefer maybe route A over B and C. That's how we would define. We generally do not assign a loss or a reward to these routes before figuring out which route I'm going to take. So that's how we are making decisions. So possibly when we are trying to think of aligning the prediction models according to the human needs, maybe we need to learn from human preferences. So if I just ask the simple question that if I give you a piece of text and I show you 3 summaries, it is much more easier for you to answer the question whether you like the summary 1 or summary 2 or summary 3, which one you like the most. But if I asked you to rate actually them in a reward or a scale of 0 to 10, it will be much more harder for you to actually scale them in a scale of 0 to 10. So the point of, similarly for movie preferences, or when we go to the eye doctor, they will also like try to understand our relative preferences over different lenses. So generally humans are always making decisions on a relative scale or in a comparative scale. And maybe a first step to design human aligned prediction models is to actually train the preference models through human preferences. Collect human preferences and then try to personalize the systems based on that. And studies actually have shown that humans are much more comfortable making decisions on a relative scale. There's studies from psychology and brain and neuroscience and cognitive science literature. So what was missing in the AI literature, more from a theoretical point of view, is a principled approach to how to formally formulate the problem of learning from preferences, and what are the foundational approaches to design efficient algorithms, and what are the guarantees of those algorithms, what are the performance guarantees of this algorithm. So because my work is more from a theoretical point of view, I tried understanding these questions from a more foundational point of view, from a more theoretical point of view. In particularly in this talk, we will figure out that how do we basically build a prediction model which will be able to personalize with respect to the human needs, and at the same time learn the prediction model effectively. We don't have to spend tons of time before training the model, and it will have probably optimal performance guarantee. So before that, so how do we actually model this problem? So this problem can be actually it's kind of a very well-studied problem in learning theory literature, or machine learning theory, or learning theory literature, or rather it's a dwelling bandits literature. It's called dwelling bandit. So assume that you have a decision space of capital K arms. This could be like your set of movies, or set of words, or set of whatever the number of actions you have in your action space. And at each point of time, as an algorithm designer, as a learner, you're supposed to query 2 arms or 2 actions. Basically, it's called arms. In the bandit literature, we called arms. So we'll select 2 arms, xt and yt, at every round. That's like 2 decisions, as if I'm showing this 2 text summaries to you, or this 2 movies to you, and then you as the user, you as who is going to give me the feedback, you're going to choose one of the 2 outcomes and say that I like that outcome over the other. So maybe I denote that outcome like by OT. This is a binary outcome because you will either like the left arm xt or the right arm yt. So I can always encode it as a binary outcome. And suppose this binary outcome actually is being generated from some underlying preference matrix that you have inside your head. I'm not going into the details of what is this preference matrix, but for the sake of, for us to be able to do the theoretical guarantee of it, we need to understand, we need to have some ground modeling for this. So now the goal could be that given this preference, given the structure of the game, how many number of times do you have to query before you figure out what is the best item, or what is the item you have, what is your favorite movie, or what is the favorite summary of the text, or whatever is the best item. One way to measure the performance of the algorithm for that could be, say, if you play xt and yt at time t, you could say that your loss of playing xt could be just the relative preference of I star over xt, and your loss of playing yt could be the relative preference of playing yt instead of I star. So this is kind of the average loss you incur for playing two different actions, xt and yt. And when you sum it over t rounds, that give you the total regret across t rounds. So the goal is to figure out how do you okay. Okay, so the goal is to figure out how do we actually drive this regret to something small, right? But there are several problems with this approach, because firstly, this preference matrix is not actually changing over time. Also, we are actually measuring the regret with respect to a fixed benchmark I star, which is impractical from a real world systems point of view. So, for example, if 4 different user comes to my system at 4 different time steps, I will assume that my preference matrix is probably changing over times. It's like P1, P2, P3, P4. And I would try to regret with respect to some dynamic benchmark and not a fixed benchmark, because this fixed benchmark might not make any sense for all the time steps. So one possible view of that could be, I can assume that there is an underlying function f which maps every context. Every user has a context. So I know the context of the user that captures the personalization, and it will map every context to a preference matrix. And now, if ft is the preference matrix at time t, I play xt and yt, and I actually compare myself with respect to it star, which is IT star is kind of what I'm maximizing on. So really, this is the action which is kind of beating me the most. So this is the action which is kind of the strongest opponent of xt and yt. So our goal was to actually give an algorithm which minimizes this regret performance in an optimal and efficient fashion. So this has been an open problem since 2015, and we, in our recent work last year, which appeared in Algorithms Learning Theory 2022, we solved this problem with an optimal efficient fashion. So this requires some min-max kind of formulation of this online learning game, which I, of course, don't have the time to cover the technicalities. And this is how the final algorithm looks like. And our final regret guarantee actually says that we can get kind of a sublinear regret guarantee of square root kt. If that makes sense, if anyone is there from the bandit literature, they will know this is kind of the sublinear regret guarantee. And yeah, so I would love to actually explain more about the methods and the technicality in the poster, but I'm not very sure if I will be virtually able to present it. But if someone is interested, please write me over my email, my first name.aslam@gmail.com. I'll be very happy to discuss more over that. Thank you.